Everyone, and welcome to Calculus Notes. This is 1.5. Today we're talking about infinite limits, and this lecture is going to round out our first chapter here. So an infinite limit, we're not going to do the formal definition, we're just going to look at an informal definition here so that we can understand what we're talking about. So it's a limit in which f of x increases or decreases without bound as x approaches c. So when we see this, the limit of f of x as x approaches c equals infinity, it actually means that the limit fails to exist. So even though we're still going to say it equals infinity or even negative infinity, that's just going to be describing the behavior as x approaches c. But infinity is not an actual number, and so the limit will fail to exist. So first, we want to determine the limit as x approaches 1. We're going to do this from the left and from the right. We're going to do this using a graphical approach. So if we look at our first example, we have 1 over x minus 1, and here's its graph, and we want to know what happens as x approaches 1 from the left. Okay, so looking at this, here is x equals 1, and from the left side as we approach this, it looks like it goes down without bounds. So this is going towards negative infinity. From the right side, it looks like f of x is going up without bound, and so this is going to be positive infinity. So because they're different, we're going to write this using two separate limits. The limit as x approaches 1 from the left is 1 over x minus 1 is negative infinity. So from the left side, we're going down. And the limit as x approaches 1 from the right side of 1 over x minus 1 equals positive infinity. So it is increasing without bound. All right, let's try number 2. So graphically, here is x equals 1. And this function from the left is increasing without bound. And the function from the right is also increasing without bound. So when they're both going to infinity, we only have to write one limit. So the limit as x approaches 1, this means from the right and from the left. So you might want to make note of that. When it's the same from the right and the left, just go as x approaches 1 of our function 1 over x minus 1 squared equals infinity. All right, go ahead and try letters C and D on your own. You can pause the video and then come on back when you're done to check your work. Alrighty, welcome back. So here in letter C, we can see our x equals 1, and as we approach from the left side, f of x increases without bound up to infinity, and as we approach from the right side, f of x decreases without bound. So we do have to write both of these limits here. So 1 minus is going to go to infinity, and then 1 plus, the limit's going to be negative infinity. In example D, you can see it's decreasing without bound on both sides, from the right and from the left. So we only have to write one limit here. The limit is x goes to 1. And here we get negative infinity. So these limits here are going to highlight something called a vertical asymptote. And it says if f of x approaches infinity, either negative or positive, as x approaches c from the left or the right, then the line x equals c is a vertical asymptote of the graphs of f. So just looking at all of these right here, our limits are all going to infinity or negative infinity as x approaches 1. And so here c is 1. So all of these vertical asymptotes are going to be at x equals 1. Okay? And we're going to abbreviate vertical asymptotes using v dot a. And we write vertical asymptotes at x equals 1. All right, and it's where the limits approach infinity or negative infinity. Now, analytically, vertical asymptotes occur at a given x value when the denominator is 0 and the numerator is not 0. So if we look up here at these examples, if I plug 1 into the equation, notice I get negative 1 over 0. So there, the denominator is 0 and the numerator is not 0, and therefore we get a vertical asymptote. So let's try this out on a couple examples here. We're going to determine all vertical asymptotes of the graphs and then sketch the graph. So what we want to try to do is use an analytic approach here. So we're going to let the denominator equal 0. And then we're going to solve for x. So here we can divide by 2 and subtract 1. Now, at this x, we have a possibility for a vertical asymptote because this is the x where the denominator is 0. But we need to test now to make sure the numerator is not 0 also. So what we're going to do is plug negative 1 back into our function and see what we get. Okay. So this is going to be 1 over, and we already said here, negative 1 plus 1 is 0, times 2 is 0. So f of negative 1 is 1 over 0. So it's important to note that we have 0 in the denominator and not 0 in the numerator. And when this occurs, we get a vertical asymptote at this x value, at x equals negative 1. So without even using a calculator, we know we have a vertical asymptote here at x equals negative 1. Now we're going to go ahead and graph this just so we can see what the rest of this looks like. So in your graphing calculator, we're going to plot this. We have 1 divided by. I'm going to put the entire denominator in parentheses, so I'll open 1 up there, 2 times x plus 1. And when we press graph, okay, we can see right here this vertical asymptote at negative 1, and horizontal asymptote looks like it's right there at 0. Y equals 0. We're going to talk about horizontal asymptotes a little bit later. We're just going to worry about the verticals for now. Okay? So this is kind of what our graph would look like. All right, let's try the letter B together. So in this case, we want to let x squared minus 1 equals 0. Now to solve for this, we're going to go ahead and factor. So we get x plus 1 times x minus 1 equals 0. And so we get x equals minus 1 and x equals 1. Now, we have to go ahead and test both of these solutions in our function to make sure we get a number over 0. All right, so let's go ahead and find f of negative 1. So that's going to be negative 1 squared plus 1 over negative 1 squared minus 1. And this gives us 2 over 0. Okay, so 0 in the denominator, 2 in the numerator. So we know we have a vertical asymptote at x equals negative 1. Let's go ahead and test f of 1. So we have 1 squared plus 1 over 1 squared minus 1. And that gives me 2 over 0. So we know we also have a vertical asymptote at x equals 1. Okay, so we're going to draw our vertical asymptote there at negative 1 and at positive 1. So graphs can have multiple vertical asymptotes. Let's go ahead and graph this on our graphing calculator and see what we come up with. Press y equals and clear. Now because we have a polynomial function in the numerator and in the denominator, we're going to want to keep parentheses around both of those in our calculator. Okay, so we have x squared plus 1 in parentheses divided by, in parentheses, x squared minus 1. And then we'll graph it. Okay, so you can see as we approach negative 1 from the left, we go up to infinity. As we approach negative 1 from the right, it goes to negative infinity. And then 1, as we approach from the left, also goes to negative infinity. And then 1 from the right goes to infinity. So we get a graph something like this. All right, I want you to try letter C on your own now. Go ahead and pause the video, and when you're finished, come back and check your answer. All right, welcome back. You can go ahead and check your work through here, and you should have found vertical asymptotes at x equals negative 1 and x equals 2. And here is your graph and the proof of why they're vertical asymptotes. All right, let's move on. Our next example says determine all vertical asymptotes and holes of the graphs of each function and then sketch each graph. Okay, so what we're talking about now is not every time that you get a 0 in the denominator is it going to give you a vertical asymptote. You might also have a hole at that x value. So here's how we're going to determine that. We do the same process as before. We let the denominator equal 0, often requiring factoring to solve. So here we get x equals 2 and x equals negative 2. And we still plug in our values here. So we want to find f of 2, 2 squared plus 2 times 2 minus 8 over 2 squared minus 4. So here we have 4 plus 4 minus 8. 8 minus 8 is 0. So now we have 0 over 0. So because we have a 0 in the denominator and a 0 in the numerator, x equals 2 is not a vertical asymptote. Instead, we're going to have a hole at x equals 2. All right, we're going to try that now with f of negative 2. So we'll substitute in negative 2 squared plus 2 times negative 2 minus 8 over negative 2 squared minus 4. And this gives me, let's see, 4 plus negative 4 is 0, minus 8, so negative 8 over 0. So in this case, because we have 0 in the denominator and not 0 in the numerator, we do get a vertical asymptote at x equals negative 2. So we'll go ahead and draw that right there. And we know at x equals 2, wherever the graph is, there's going to be a hole. So let's go ahead and graph this. Okay, polynomial on top, so parentheses. X squared plus 2x minus 8, close your parentheses, divided by x squared minus 4. Now I did this on purpose. I forgot to put parentheses. And what do you do if you did that? Well, you could press clear, but then you're going to have to retype everything in. So there's this little function called ins, which is insert. So you just move your cursor over to where you should have the parentheses. Okay, so you're going to put it over the x, and if you just started typing, it would replace the items. But we want to insert a parenthesis. So you're going to press second and then insert. You can see it's kind of blinking funny there. And now when I press my parentheses, lo and behold, it inserts it. So hopefully that can save you some time if you forget to put those parentheses. And as soon as you start going over to the right or left, insert is now gone. We can close the parentheses there. All right, so let's take a look at the graph. And you can verify here that we do have a vertical asymptote at x equals negative 2, and we don't have a vertical asymptote at 2. Now again, in the graph, it looks like it's continuous right there, but we know there is a hole at x equals 2. So we'll go ahead and sketch this graph. So at x equals 2, we have a hole, and then it continues on. All right. Go ahead and try letter B on your own. And just a suggestion, when you're plotting this, go ahead and let everything go by 2's in your graph. So 2, 4, 6, so on and so forth. All right, so give B a try, and then pause the video. Come on back when you're ready to check your answer. Alrighty, welcome back. You can go ahead and check your work, and we found negative 5 and 5 to be where the denominator equals 0. When we plug in 5, we get 0 over 0, so x equals 5 is not a vertical asymptote, and rather there's a hole at x equals 5. And when we try f of negative 5, we get 50 over 0, so there is a vertical asymptote at x equals negative 5. And here's your graph showing the vertical asymptote. So as we approach negative 5 from the left, it goes to infinity. As we approach negative 5 from the right, it goes to negative infinity. And you can see the hole right here at x equals 5. All right, now our final example is going to be finding some limits, and we're going to talk about how vertical asymptotes can help us there. What we're trying to find the limit as x approaches 1 from the left. And we're going to go ahead and try direct substitution here. So we get 1 squared minus 3 times 1 over 1 minus 1. And this gives me 1 minus 3, which is negative 2 over 0. Now, this tells us that direct substitution fails to find the limit. Okay. Now, before, we would have had to go ahead and try to factor this or figure out what's going on at this point to see if the limit could still exist. However, now that you know something about vertical asymptotes, when we have a 0 in the denominator and not 0 in the numerator, you can say that we have a vertical asymptote at x equals 1. So now we have this right here. So we know as 1 approaches from the left that this is either going to go to infinity or it's going to go to negative infinity. So we're not going to get a limit, but we do want to determine whether it's infinity or not. So we're going to go ahead and try to find the limit from the left. We can either do it graphically or we can do it numerically. What do you guys want to do? I'm going to do it graphically since that's what we've been doing. Now, another thing that can sometimes save time is when your polynomial is similar to what you just typed in. So x squared minus 3x, we can alter this. So the plus would need to become a minus. So we just hit minus. The 2 needs to become a 3, so it just replaces. And then we're going to delete the negative 8. So delete, delete. Then in our denominator, we don't want that exponent, so we're just going to delete it, and we want x minus 1. Okay, so maybe it'll save you a little bit of time. Let's draw our graph and see what's happening there. Okay, again, you can see our vertical asymptote here. And so the limit as we approach 1 from the left is going to infinity, and the limit as we approach 1 from the right is going to negative infinity. All right, I want to take a look at letter A above, determining the vertical asymptotes and holes of the graphs. And I want to look at it through a little bit different lens than what we did in the example. So here's our function again. Another way to solve this is by factoring both the numerator and the denominator. So we get x plus 4 and x minus 2, because 4 times negative 2 is negative 8, and 4 minus 2 is 2. And the denominator, we already factored above. It was x plus 2, x minus 2, our difference of squares. Now before, we noticed that the denominator would equal 0, so we set it equal like this. So it equals 0 when x equals negative 2 or x equals positive 2. Now we determined by substitution that x equals negative 2 gave us our vertical asymptote, and x equals 2 gave us a hole. Now when we're talking about this, a vertical asymptote is which type of discontinuity? Well, this is a non-removable discontinuity right here, where a hole is a removable discontinuity. So let's go ahead and look up at our function again and see if we can determine why we can also use the words removable and non-removable when looking at our function. So this factor right here, the x plus 2, gave us our vertical asymptote, which is non-removable. Now if we look in this function, can we cross off the x plus 2? Can we remove it from this equation? Well, no, it's non-removable. Now let's look at our second factor here, x minus 2. And notice that x minus 2 gave us a hole at x equals 2. Now looking at our function, can we remove this from the function? Well, yeah, we can. So the x minus 2 would cancel here, and so therefore it is a removable discontinuity. Okay, so you're going to get vertical asymptotes at the non-removable factors, and you're going to get holes at the removable factors. All right, that's all of the notes for today, and I look forward to seeing you all in class. Thanks for watching.